Hello and welcome back to educator.com and welcome back to biochemistry. So today we're going to start talking about acids and bases. This is going to be a reasonably quick review because again we just want to get our feet wet, get used to some concepts from general chemistry before we actually dive into the biochemistry proper. So acids and bases. Acid-base chemistry is profoundly important. We're going to be going through most of the stuff that you've seen. We're going to be talking about pH. We're going to be talking about how acids and bases behave. What I'd like you to take away from the notion of acid-base chemistry is how acids and bases actually behave, and the idea that the only thing that moves in an acid-base reaction is the proton, is that hydrogen ion. If you can concentrate just on that aspect, you can use what you know about your intuition that you've gained from general chemistry and from organic chemistry to actually understand a huge amount of biochemistry. Don't get lost in the details here. I mean, yes, the details are important, but what's important is understanding that it's only a proton that's moving. That's it. That's the only thing that's going on here. That's the important part to take away from this. Okay, let's go ahead and start our review. Let's go ahead and begin with water. So, let's begin with H2O. Okay, so H2O, water in solution, actually dissociates a little bit. It releases a free hydrogen ion and it releases a free hydroxide ion. So we write that this way, as H plus OH minus. Now, you remember from general chemistry that now we want to be able to have some sort of a numerical measure of the extent to which something dissociates. In other words, how much H plus, how much OH minus is floating around in water. Well, you remember there's something called the equilibrium constant. You have some reaction. What you do is you take the concentration of the products raised to their stoichiometric coefficients divided by the reactants raised to their stoichiometric coefficients. Now let me go ahead and put some state symbols here. This is AQ and this is AQ. And you remember, of course, when we have liquids or solids, they actually don't show up in the equilibrium expression. So in this case, our KEQ is going to equal the concentration of H plus times the concentration of OH minus. But again, this is liquid, so it doesn't show up in the denominator, so that's all. Now we call this, because it's for water, we give it a special symbol, Kw. We've measured this, and it's actually equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius. So at 25 degrees Celsius, this ion product constant, this dissociation constant for water, happens to be 1.0 times 10 to the negative 14. That's a very small number. What that's telling you is that most of it stays as water, but a little bit of it, very little, dissociates into that. Okay, that's it. So this is a very important relation. Now, in any and every aqueous solution, the hydrogen ion concentration times the hydroxide ion concentration has to equal 1.0 times 10 to the negative 14. In other words, if the hydrogen ion concentration rises for some odd reason, the hydroxide ion concentration drops because their product has to equal a constant. That's what this whole idea is. A constant is something that doesn't change. The particular values of the individual species involved in the constant, they might change, but their product doesn't change. So if one goes up, the other has to go down. Okay. Now let's introduce something called the p-scale. You already know this, but we will mention it anyway. So we talk about pH, and that's equal to negative log of the hydrogen ion concentration. pH was used, again, hydrogen ion concentrations are generally very small, things like 2.6 times 10 to the negative 3, very tiny numbers. So instead of dealing with those numbers, they developed this idea of a p-scale because they wanted to deal with numbers that are just more natural, like 6.2, 10.6, things like that. It doesn't really matter. I personally prefer to deal with concentrations directly as opposed to taking the negative logarithm of them and using the p-scale. But in biochemistry, they tend to use the p-scale almost exclusively. So that's all it is. It's just the negative log of whatever concentration. We also speak of a POH. That's the negative log of the hydroxide ion concentration. You can also talk about, let's say, PCl. That's equal to the negative log of the chloride concentration. It could be P anything, so P scale. But most of the time, we talk about pH. We pick one thing to discuss as our standard in a particular aqueous solution. We've chosen the hydrogen ion concentration as the standard against which other things are measured. Okay, so let's see. So if the hydrogen ion concentration times the hydroxide ion concentration in any aqueous solution is equal to 1.0 times 10 to the negative 14, well, in terms of pH, if I take the negative log of both of these, I get the following. I get the fact that the pH plus the POH of an aqueous solution is equal to 14. They're the same thing. One deals with concentrations directly, the other deals with a different representation of concentration. That's all. Okay, so a pH of, well, actually I'll introduce that in just a second. Okay, so let's see what we have here. So let's do an example just real quickly. Okay, the pH of a glycine solution. Glycine is an amino acid, and we'll get to that in just a couple of lessons when we start to discuss proteins, is measured to be 5.4. Okay. The question for us is, what is the hydroxide ion concentration? What is the hydroxide ion concentration in the solution? Okay. Well, nice and easy. We just use this right here. That's our basic relation. So, okay, the pH. So if the pH of our solution is equal to 5.4, well, that implies that 5.4 equals negative log of the hydrogen ion concentration. That's the definition, right? So let's go ahead and take the antilog, okay, raise it to the power. That means the hydrogen ion concentration is equal to 10 to the negative 5.4, right? Move the negative sign over, antilog, just take 10 to that particular power. And when we do that, we get 3.98 times 10 to the negative 6 molarity. So the concentration of hydrogen ion in this particular glycine solution is 3.98 times 10 to the negative 6 moles per liter. Okay, well, we know that the hydrogen ion concentration times the hydroxide ion concentration is equal to 10 to the negative 14, right? 1.0 times 10 to the negative 14. Therefore, the hydroxide ion concentration equals 10 to the negative 14 divided by the hydrogen ion concentration, which is 3.98 times 10 to the negative 6. And when we do this calculation, we get, what do we get? 2.51 times 10 to the negative 9 molarity. That's it. Nice and simple. Basic relation. Hydrogen ion concentration times the hydroxide ion concentration at 25 degrees Celsius is 10 to the negative 14. If I have one, I have the other. If I wanted to go to pH, if I wanted to, let's say, do the POH, what I would get is the following. POH, I would just take the negative log of this hydroxide ion concentration, and I get 8.6. Nice, straightforward, nothing strange going on here. Okay. So now let's talk about the pH scale. Any pH from 0 to 7, we call that an acidic solution. A pH of 7 is called a neutral solution. And a pH of 7 to 14 is called a basic solution. What that means is, in an acidic solution, the hydrogen ion concentration is greater than the hydroxide ion concentration. They're not equal. In a neutral solution, the hydrogen ion concentration actually equals the hydroxide ion concentration. 10 to the negative 7. 10 to the negative 7 equals 10 to the negative 7. 10 to the negative 7 times 10 to the negative 7 equals 10 to the negative 14. That's where the scale comes from, 0 to 14. It's based on that. Actually, it's based on that number. And a basic solution is when the hydrogen ion concentration is less than the hydroxide ion concentration, or another way of thinking about it, when the hydroxide ion concentration exceeds that of the hydrogen ion concentration. But no matter what they are, they multiply to 10 to the negative 14 at 25 degrees Celsius. Different temperature, it's a different kW. Okay, good. So now let's go on and discuss. So strong acids. Strong acids are acids that completely, ooh, it might be nice if I actually knew how to write here. Oh my God, what is happening? Let's try this again. There we go. Strong acids are ones that completely dissociate when put into water. In other words, if I take some hydrogen chloride, and if I drop it into water, what happens is that it actually becomes an aqueous solution of hydrogen chloride, and then it completely dissociates into H plus and Cl minus. There's actually a two-step process. I take the pure hydrogen chloride. See, this is the thing. When we speak of things like HCl, H2SO4, H3PO4, we refer to them as acids because 100% of the time in our dealings with them, we're going to be dealing with them as solutions. As solutions, they are acids. They're acids when they dissociate. When they're like this, in pure form, they're not acids. We still name them as such, but what happens is when we speak about acids, we're speaking about an aqueous solution. We've taken this thing and we've dropped it into water, and then first of all, it becomes solvated, water surrounds it, and then water takes it apart. It breaks up. So anything that completely dissociates, in other words, when there's no HCl left, we call it a strong acid because it completely separates into free ions. Another example would be HNO3. I'm going to skip this part. H plus NO3 minus. A strong acid, when you drop this into solution, or when you drop this into water, into a solvent, all of this comes apart. There's none of this left. There's only H plus floating around and NO3 minus floating around in a nitric acid solution. That's what's happening. Strong acids don't have an equilibrium constant precisely because there's no reactant left over to be used as the denominator of the equilibrium constant. So anytime, if you're looking through a list of equilibrium constants for acids, then if it's not there, it's a strong acid. That's pretty much how you tell. Okay. So a strong base, same thing, except instead of complete dissociation. A strong base, instead of producing hydrogen ion, they produce hydroxide ion. So an example would be sodium hydroxide. It completely dissociates into sodium plus hydroxide ion, OH minus. That's it. There's none of this left. The only thing you have floating around in a sodium hydroxide solution is a bunch of sodium ions, which are harmless, and then you have the hydroxide ions, which are not harmless. Okay, now we're going to get to the important stuff, weak acids and bases. This is where everything gets really, really exciting. So weak acids and bases. Well, weak acids and bases, exactly what you think it is. Weak acids and bases are ones that don't completely dissociate. However, before I discuss that, I'm going to write down the thing that I mentioned early on before we started this lesson, the only thing that moves in acid-base reactions is H+, the proton. Remember that. The only thing that moves is the H+. That's it. H+ is going to bounce from one species to another species. The species that it goes away from is the acid. The species that actually it goes to is the base. That is all that acid-base chemistry is about. The rest is just math. Okay. So let's talk about weak acids. I'm actually going to start this on another page, and I'm going to go to a blue ink. So a weak acid. And I'm going to start with an example as opposed to a definition. So, and again, a weak acid is one that just doesn't dissociate completely. So I'm going to use hydrofluoric acid as my example. HF plus H2O. When I take hydrogen fluoride, I drop it in water. A reaction takes place between hydrogen fluoride and water. Hydrogen fluoride gives up its hydrogen ion. Water takes the hydrogen ion. This is the acid. This is acting as the base. What you get is the following. H3O plus F minus. Now, I'm going to write this in another way. I wrote it this way simply because the reaction that's actually taking place is this. Anytime there's an acid, there's also a base. The acid is the thing giving the hydrogen ion. The base is the thing taking it. In this reaction, hydrogen fluoride is acting as the acid. H2O is acting as the base. What you get is a hydronium ion, and you get F minus. There's another way that we actually write this, which tends to be a little bit more popular with in biochemistry. When dealing with weak acids, they generally drop this H2O part, and they write it like this. HF, H plus F minus. They say that this hydrogen fluoride dissociates a little bit to produce some hydrogen ion and some fluoride ion. Now, notice this equilibrium arrow. This is an equilibrium. It doesn't go to completion. All of it doesn't dissociate. In fact, for weak acids, most of it does not dissociate. Very little, in fact, dissociates. So we can write an equilibrium expression for this. By the way, this is AQ, and this is AQ, and this is AQ, so everything shows up in the equilibrium expression. The equilibrium expression for an acid is, for this one, is H plus F minus. Actually, for all weak acids, it's going to be the hydrogen ion concentration times the conjugate base concentration over the concentration in moles per liter of the original acid. So it's products divided by reactants. Well, it's an equilibrium expression, but because we're talking about the standard acid reaction, we actually call it Ka, A for acid. That's it. It's called the acid dissociation constant. Dissociation constant. And there's lists of acid dissociation constants for the different weak acids. Hydrofluoric acid, phosphoric acid, nitrous acid, whatever it is. Okay, in this particular case, the Ka for hydrofluoric acid happens to be 7.2 times 10 to the negative 4. Okay, this is very small. Okay. That means that this is a tiny number and this is a big number. What that means is that very little hydrogen fluoride actually dissociates to produce hydrogen ion in solution. Yes, it is an acid, and yes, it does dissociate, and yes, the pH of this solution is going to be less than 7, but it's not going to be altogether that much less than 7. It's a weak acid, not complete dissociation. There is an equilibrium that takes place here. Okay, so let's do an example. Example 2. So let's do phosphoric acid, because that is a very, very important weak acid in biochemistry. So phosphoric acid is H3PO4. Now, when acids dissociate, they dissociate one hydrogen at a time. In this particular case, it's not just going to give up 3 hydrogens. It's going to give up 1 hydrogen, then another, then another. there is an equilibrium expression for each dissociation. So for phosphoric acid, what you have is the following. When it dissociates, oh, and by the way, we're probably going to end up doing this version of it without explicitly mentioning the water, but it's important to remember that it's water that's actually reacting. So H plus and H3O plus, they're interchangeable. They're the same thing. There is no H plus floating around in solution freely. What it is, it's an H plus that's attached to a water molecule. So these are the same thing. This is just a different way of writing it. Here, we write this version of the equation simply to explicitly show that water is acting as the base in this acid-base reaction. So H3PO4 dissociates into H plus. Let me go back to blue so that I'm consistent here. Blue dissociates into H plus H2PO4 minus. It has a Ka1, a first dissociation constant. Well, now H2PO4, that can also dissociate. It has a hydrogen ion that it can give up, and it does so under the appropriate circumstances. And it breaks up into H plus HPO4 2 minus. It has a acid dissociation constant associated with this reaction. It is called the Ka2. Sorry about that. Well, HPO4, there's still a hydrogen ion, so under the appropriate conditions, it too can dissociate to produce H plus and PO4 3 minus, the phosphate ion. It too has an acid dissociation constant. That's the Ka3. So that's it. Let's go ahead and take a particular reaction as our example and do a little bit more with it. So let's just go ahead and take the second dissociation of phosphoric acid. So our Ka2 is going to be the concentration of HPO4 2 minus, the reactants, times the H plus concentration divided by the H2PO4 minus concentration. That's it. And in this particular case, the second acid dissociation constant happens to be 1.38 times 10 to the negative 7. Very, very, very small. Okay. So again, let me go ahead and write this out explicitly using water as our other reactant, H plus HPO4 2 minus. In this particular case, the H2PO4, this is acting as the acid, because it's the one that's giving up the hydrogen ion. The water is acting as base, because it's the one taking the hydrogen ion. Okay, now there is a certain nomenclature that's used. Anytime you have a particular species, if it's the one giving up, we call that the acid. The thing that it turns into, once it's actually given up its hydrogen ion, which is this thing right here, we call it the conjugate base. And what that means in this particular case is, because if we were to look at this reaction the other way around, in other words, if we were to start with this, now what happens is, oops, this is not H plus, this is H3O plus, because I actually used H2O here. Now what happens is, if I started with the HPO4 2 minus and wanted to look at it from the perspective of this going that way, then this is actually going to act as the base, and it's going to be H3O plus that's going to act as the acid. This is going to be the proton donor, this is going to be the proton acceptor. Now, acid conjugate base. However, when we're looking at it from this perspective, when this is the reactant and this is the reactant, what's acting as the acid is the H2PO4 minus. What's acting as the base is the H2O. So again, nomenclature is actually not that important. What's important is that you understand what's giving up the hydrogen, what's taking the hydrogen. The giver is the acid, the taker is the base. That's what's important. Okay. And again, notice the only thing moving here is the H plus. All right, now let's talk about weak bases. Weak bases. Okay, let's just say first of all, a base, whether weak or strong, is something that produces hydroxide ion in solution. Well, a strong base does it directly. Strong base produces OH minus directly. And by directly, I mean it just dissociates, and when it dissociates, hydroxide just goes into solution. An example of that would be potassium hydroxide. When I drop that into solution, I get K plus and OH minus now floating around in solution. Notice the single arrow. There's no equilibrium here. There's none of this left. When it dissociates, it's all this and it's all that. A weak base. A weak base produces hydroxide indirectly. Produces hydroxide indirectly. And here's the reaction. I'm going to use ammonia as our base. Oops. No, we definitely don't want that. These crazy lines that show up here. Okay. So we have NH3, ammonia. When you take ammonia and you drop it into water, a reaction takes place between the ammonia and the water. I'm going to write the water as HOH. That's my personal way of doing it because it actually makes more sense to me. So I don't write H2O, I write HOH, and you'll see why in a second. In this particular case, an H from the HOH from water, now water is going to act as the acid. It's going to give up one of its hydrogen ions, and ammonia is going to take it. So in this case, water is acting as the acid, this is acting as the base, and what you get is the following: NH4 plus OH minus. So again, we've produced hydroxide in the solution, however we've done it indirectly. A weak base is something that actually extracts a hydrogen ion from water to leave a hydroxide behind. That's why I write it as HOH. I don't like writing it as H2O. It's just a personal thing. You can do it any way you want. But this is the reaction that's taking place. Very, very important. The generic reaction is this. Base, any base, B plus water goes to BH plus OH minus. This is the generic. Okay, in this particular case, my B, my base is NH3, ammonia. It could be anything, any weak base, anything that behaves like this. Okay, we can write an equilibrium expression for this. Let me rewrite the expression. So we had ammonia plus water produces ammonium plus hydroxide. Okay. There is a way of writing an equilibrium expression for this. It is products, NH4 plus times OH minus divided by NH3. Water does not show up because water is a liquid. Okay? Now, when the base reaction is taking place, we call it Kb. This is called, now they call it, I call it the base association constant. And the reason I call it association constant instead of dissociation constant, or just the base constant, is because what's happening is that the base is actually associating with an H to become NH4 plus. So base constant, acid constant, what's important is the reaction that takes place. Okay, let's go ahead and do an example of another base. Example 3, so pyridine. Pyridine, which looks like this. Okay. Pyridine shows up. Actually, it doesn't really matter. Pyridine is a weak base. And notice, as a nitrogen, it's going to be a common theme. Weak bases are pretty much going to have nitrogen in them. Is a weak base. Let's see what its reaction as a base looks like. Okay, so we have our pyridine, and actually what I'm going to do is I'm going to write it as PYR. Pyridine plus water is going to be pyridine H plus plus OH minus. That's it. The Kb for this is going to be the concentration of pyridinium ion times the concentration of hydroxide ion divided by the concentration of pyridine. And in this particular case, it's equal to 1.7 times 10 to the negative 9. Again, this is a small Kb. That means that the reaction has not gone very far forward, that it's mostly this way. That in a solution, in a pyridine solution, most of it is in this form. There isn't a lot of this. There isn't a lot of this. Now the pH is still going to be greater than 7 because you've actually you've taken water, which is pH 7, and you've created this extra hydroxide ion, floating around. So the pH is definitely going to go up. In other words, the hydroxide ion concentration went up. That means the hydrogen ion concentration went down. The product still equals 10 to the negative 14, but now the concentration of hydroxide is higher. So the pH is above 7. Okay. Now let's see what we can do. So again, when you're seeing it from the perspective of an acid, when you're doing the acid reaction, you're going to have something called a Ka. When the particular species that you drop into water behaves as a base, like pyridine or like ammonia, you're going to look at it as a base and you're going to have a Kb. Okay. Now let me write a couple of things here. Let me go to a different page. Now, when a species has an H plus, it can give up it is in its acid form. When it can accept an H plus, it is in its base form. So this whole idea of acid or base is not absolute. It's not that something is an acid or something is a base. It just depends on how it's behaving. If it's in the particular form where it can actually has a hydrogen to give up and it does give it up, it's behaving as an acid. But if it's the other way around, if it turns around and actually takes a hydrogen ion, then it's acting as a base. So the same species can be both. It just depends on your perspective. So again, in science, we need a particular perspective. We need a point of reference from which to measure something, from which to look at it. So that's what we're doing here. But it just depends on what's happening in the particular situation. So for example, NH3, well, ammonia, when it's behaving as ammonia, is going to behave as a base. But if I happen to have, let's say, some ammonium chloride salt, NH4Cl, and I drop that NH4Cl into water, now what's happening is that now there's a bunch of ammonium floating around in solution. Well, now this species is not going to behave as a base. Now it has that extra hydrogen ion and it's going to actually give it up. Now it's going to behave as an acid. So acid-base behavior is based on behavior. It's not that a particular species is an acid or a base. Acid-base reactions have to do with what's happening, what's giving the H, what's taking the H. In this particular case, this NH3 and this NH4, here is the base form, here is the acidic form. For our purposes, since most of the time we deal with NH3, we have listed, in the list of equilibrium constant values, we've listed it under the heading of a base, simply because we tend to think of it more as a base, but it has an acid version. Hydrogen fluoride. Well, we think of it as an acid. Well, it is an acid, But when it's in this form, when it's already lost it, and when it's behaving this way, it's actually acting as a base, because in this case, now it's going to take the hydrogen from something else. So for example, if I had a sodium fluoride salt, and if I took that sodium fluoride and if I dropped it in solution, now what I have floating around in solution is a bunch of sodium ions and fluoride ion. Well, F minus doesn't have an H to give up. However, this F minus is going to end up reacting with the water in solution. It's actually going to steal a hydrogen ion from the water. So in this case, it's going to be acting as a base to turn back into its acid form. So that's what you want to think of. Two sides of a coin, heads or tails. At any given moment, we have to decide which perspective. Is it behaving as an acid or is it behaving as a base? So it can do both depending on what's happening. Now, can we write well, actually we just talked about that. Yes, we can write these the other way. So what's important here is perspective. When it undergoes this reaction, let's just say HA plus H2O goes to H3O plus A minus, this is the acid reaction. That's it. But if I write it this way, if I say A minus plus H2O goes to HA plus OH minus, that's the base reaction. Be very clear about the species here. Here, HA, it's behaving as an acid. It's giving up its hydrogen to water to produce hydronium and this other species, the base version of its species. Here, if I take the A and if I drop it into water, what it does, it steals H from the water to produce hydroxide and to produce HA. Now it's acting as a base. So it just depends on the perspective. That's what's going on here. Okay. And let's see, one final comment. So this idea of Ka and Kb, when a species is behaving as an acid, it has a Ka. When a species is behaving as a base, it has a Kb. There is a relationship between these two. Ka times Kb equals Kw, equals 10 to the negative 14. So let's just use hydrofluoric acid as our example. HF plus H2O goes to H3O plus F minus Ka. We said that the Ka here, let's go back. What did we say the Ka of HF was? 7.2 times 10 to the negative 4, I think. Right. 7.2 times 10 to the negative 4. That way. But if I happen to, let's say, take a sodium fluoride salt, and if I happen to run this reaction, now, because it's acting as a base, I have to, if I do any math with it, I have to use the Kb, not the Ka. Well, the Kb happens to equal the Kw over the Ka. Now, I just wanted to introduce it here towards the end. I'm actually going to be discussing more of this in the next lesson, so don't feel like this just, wait a minute, what's going on here? So I am going to be beginning the next lesson with a discussion of Ka, Kb, and the relationship between those two, and we'll do some more problems. Until then, thank you for joining us here at educator.com. Take care. Bye-bye.